Okay, so there's two situations when you're dealing with magnetic fields. There's going to be situations where there's charges moving through external magnetic fields. So here's an external magnetic field that's being produced from some outside source, and there's a charge moving through it, and then there will be a force felt on the moving charge. And then here, it's the same thing, except the charge is the current, right? There's a bunch of charges. Magnetic field is being produced externally from some outside source, right? It's cutting through the wire, and then there's going to be a force on the wire pushing it up. So for external magnetic fields, you're using the three-finger rule, where the finger in this example is going to be the direction of the charge, a positive charge, right? Use your right hand for positive charges and left hand for negative charges. So magnetic field's moving this way, and then the force is moving up, right? That's what I have here, okay? So you'll be using the three-finger rule for these. Now notice how the magnetic field and the direction of velocity of the charge are always on the same sheet of paper. You see that? And the force is essentially coming straight up out of the sheet of paper, no matter what the angle is. So like here, you can see how the angle gets smaller between the magnetic field and the velocity. So the external magnetic fields are moving this way, and the velocity's kind of coming across it at a smaller angle. Well, there's still a force coming straight up out of the page, okay? But it's not as strong, so it loses strength. And then same thing, I'm just showing it here as current through a wire, right? External magnetic fields pierce through it, the force is going up, and it's not as strong as it was when the angle was 90 degrees. So as that angle gets smaller, the force gets smaller, and eventually it disappears, right? When the magnetic field and the direction of the velocity or the current are the same, what is sine of 0 degrees? It's 0. So 0 times anything is 0, so there's 0 force. Now notice how I said that the magnetic field and the velocity direction are always on the same sheet of paper. So if we started to, let's say the velocity was kind of going uphill, so we were kind of like this, right? We were on a sheet of paper like this, kind of flat, and now I kind of lifted it up. So the velocity is kind of going up. Well, the magnetic field and the velocity are still on the sheet of paper, and the force is now still coming straight up off that sheet of paper. So that force will always be coming straight up off that sheet of paper. Okay, so now let's look at some other examples, what happens, because these lines only represent what's happening at this point, when the charge is moving and we take a snapshot at this point, where like it's moving this way, magnetic field's that way from external production, and the force at this point is going up. Now what if the charge, right? What if the charge is free to move? So at this point, it's moving this way, but there's a force pushing it up, and the magnetic field doesn't change, right? The magnetic field is still going from front to back in all these scenarios because it's being produced externally from some outside source. So as the particle moves from here to here, well, there's going to be a new force pushing it up this way. And then when it gets to here, it'll be pushing it up that way. And when it gets to here, it'll be pushing up that way. And when it gets to here, it'll be pushing up that way. So the force is always going to be 90 degrees to that sheet of paper, essentially. So the sheet of paper, right, as this moves here, and then it moves from here to here, you can see how the sheet of paper kind of lifts up, right? That sheet of paper kind of lifts up. And so the force is now going this way, and then the sheet of paper lifts up more, or the sheet of paper starts spinning. So essentially what I'm saying is the force is going to be pushing a moving charged particle towards the middle, towards the center, to a central point. So the velocity wants to keep going this direction, but the force is pushing it upwards, and so it makes it change direction every moment it moves. Okay, now here is the force for the moving charge particle. Okay, and what do we know about this? We're changing it to the current form. Okay, so we're looking at this formula here. And how do we get this from this? Well, current equals charge over time. So how much charge is moving over a point in time, over a certain amount of time, right? So if there's 10 charges per second moving across, that gives you a certain amount of current. If there's 1,000 charges moving per second, well, that's a lot more current, right? So it's just how much charge over how much time. All right, and so if we solve for Q, it's Q equals IT. Now, what is velocity? Velocity is distance over time, or length over time. So you have Q and V. You replace them with what they are, right? IT and L over T. So Q is IT, V is L over T, T's cancel out. You got ILB sine theta, which is this scenario. Now, notice the charge that was right here moving through this wire isn't curving upward because it's confined to a wire, right? So the force on the wire will be up at every point because the velocity direction of the charge that's confined in the wire doesn't change. So when there's a wire, the whole wire itself is just going to move up. Now, with a single charged particle moving through an external magnetic field, you can use this equation, and also you can represent the force that it's experiencing by the centripetal force. So this is the magnetic force. Here's the centripetal force. So that would be m time. So the mass of the particle times velocity squared over the radius from here to here. So this is the radius. You can also represent this charged particle moving around as centripetal force. So you can set these two equal to each other and solve for some things. So just remember these three formulas whenever you're dealing with external magnetic fields. Okay, and if you were to set these two equal to each other, so like since the force on this particle going up is the same as the centripetal force, right? You can say QVB equals mv squared over r. This v cancels out with that v, and then you can say QB equals mv over r. Okay, and so if you know 4 out of the 5 variables, you can solve for the last one, right? If you know Q, B, R, and V, you can solve for M. If you know Q, M, V, and R, you can solve for B, right? So that's just some situations you might see when it deals with the 3-finger rule and the Lorentz force. Now back here, okay, there is no external magnetic field being produced anywhere. This is just charge moving through wires. So charge is not moving through an external magnetic field. There's no force. You use the curled finger rule for this one. The magnetic field produced by the moving charge. So the magnetic field in these situations is actually produced by the moving charge. So this is where we use the curled finger rule, and it's interchangeable. So when the charge is moving linearly, the thumb represents the motion of the charge and the fingers represent the curl of the magnetic field. If the charge is moving in a circular path, right? If it's moving in a circular path, the fingers represent the direction of the moving charge and the thumb would be the magnetic field. So they're interchangeable. So let's look at this example real quick. And this is where all the magnetic field formulas are to let you know the magnetic field strength. So if the charge is moving this way, right? Let's say that let's say that the current is moving to the right. You would use right hand rule, thumb would be pointing this way, magnetic field would be coming around, right? Be coming around the back into the front, okay? And then you could see if you were to measure the magnetic field strength from here up to say here, that's a radius r. So the magnetic field strength at this point, so I'm gonna put magnetic field strength in produced, it's always gonna be mu sub naught times the current divided by, now in the linear wire, it is 2 pi r, okay? That will tell you the magnetic field strength at this point. If you know the strength of the current and you know the distance that you want to measure away from that wire, you'll get the magnetic field strength at that point along, and that'll tell you the strength around this entire line, this outer magnetic field line. Now, let's say the current is going this way, right, in this wire. So you have to use your curved fingers to say which way is it going. So if it's going around the back and then coming up the front, right, it's coming up the front, it's going around the back, right, you would be saying this is the direction, the fingers are the direction of the current, and the magnetic field would be going out this way, right? It'd be moving out this way through this entire wire. It'd be moving out this way. Okay, so that would be the magnetic field direction. Now here is the formula for that. Magnetic field produced, this is for a solenoid. It is, so it's going to be mu sub naught times I, that's going to be always in the mix, times the number of turns, right? There's like 5 here, but number of turns times the length of this solenoid. So times its length, or divided by its length, I'm sorry. Now what if this solenoid, right, the solenoid itself, the bar that it's wrapped around, gets turned into an entire circle? Well, it's still mu sub naught times I over number of turns, right? So this has a number of turns in the wire over the length of the wire. So what is the length of the wire here? What is the length of a circle, right? The circumference of this wire, this bar, I'm sorry. Length of the bar. So not length of the actual wire itself, but the length of the bar, because this L represents the length of this bar, right? So the length of this bar all the way around would be, it'd be mu sub naught I times, again, N over L. But what is L here? L is 2 pi r. Okay, now r is the distance from the bar to the center of the toroidal solenoid. Okay, now I don't know if you'll see that or not, but anyways, now what if you have a current carrying wire, current's coming in, and it's in a coil, so it's not wiggling down like this, it's just staying in a coil going around turns that are tightly packed, right? Oh yeah, that should be going this way. Yeah, I drew that the wrong way. So that'd be coming in this way, curling around, and then exiting out this way, right? So if it's going up that way and curling around, the magnetic field will be coming out this way. So the magnetic field at the center, so this formula is for at the center of this coil, it's going to be B equals, so it's just like this one, except there's no pi symbol. Mu sub naught I over 2r. Okay, so those are the magnetic fields that are being what? Produced, right? Produced by moving charge. There's no external magnetic fields cutting through this. So that gives you some, at least some understanding of the two scenarios and which way to use the right-hand rule, right? Use a 3-finger rule for a charge moving through an external magnetic field, and there's a force in there. Here, you use the curl finger rule. There is no force anywhere. You're just talking about the magnetic field. And each magnetic field has a different formula. Whereas up here, the magnetic field doesn't have a formula. They'll just be giving you the value of the magnetic field strength to plug into this equation. So they may say there's an external magnetic field with a strength of like 5 Teslas or something, you know? And down here, they'll be giving you, if you're looking at this one, they would have to give you 2 of these 3 variables, right? R, I, and B. They'd have to give you B and R, or I and R, or B and I, and you'd have to solve for R. Since these are constants, right? They would have to give you 2 out of those 3 to solve for the third. And then down here, there's 1, 2, 3, 4 variables. So they'd have to give you 3 of the 4 variables to solve for whichever one. So I think there was one problem. They were saying how many turns is in this wire when they gave you how much the magnetic field was, how much the current was, and how long the wire was, and you had to solve for N. So you just pretty much get everything over here, you know, multiply both sides by L, divide by mu sub naught I, and you got N. So anyways, that is essentially what is happening. Now the magnetic field, I forgot to say, the magnetic field strength here is coming straight out at us. Hold on, let's see, is that right? No, I'm tripping. Okay, magnetic field is not in here. That is not the magnetic field. The magnetic field in here is 0. It's 0. The only place that the magnetic field is being produced is through this bar. And it would be this way. It would only be going this way, because when you use the right hand rule at the base there, right, it's curling around and coming back around, and so your thumb's pointing in that direction. So the magnetic field is inside of the bar. It's 0 out here, and it's 0 inside in between here. The only magnetic field existing is inside there.